So it's my pleasure to introduce you, Mathis Richter, that's currently working at Intel and is a former postdoc PhD master. And I also think you did your bachelor thesis at our institute.
I did, yes.
So probably the one of the longest records of membership at the Institute of Neurocomputation. Also one of the masterminds behind CEDAR and behind the beautiful model of spatial language that Daniel hinted in his talk. So now he's working at Intel in neuromorphic computing, so bringing DFT to the Intel's neuromorphic chip. And I think the best thing is to start. I think pass to Mathis now.
Thanks all for these kind words. Yes, I was with the INI for a very, very long time. And I've been with Intel for, I don't know, it's 1.5 years or so, something, in the neuromorphic computing lab. So Intel is this large corporation, right? Part of that is Intel Labs, that's the research arm. And that is organized into labs. And one of these labs that's about 35 people, maybe 40 at the moment, is the Neuromorphic Computing Lab, where we research neuromorphic hardware and software and algorithms. And in that group, I work with Julia Sanemiska, whose name you may have also heard during the summer school. She was also a PhD student of Gregor's. And we work on applications for neuromorphic devices. And I want to maybe give you a perspective from that view. Myself having a background in DFT also, and I know the sort of research that you do, it's fundamental research, but now I'm in a role where we are looking at it from a different perspective, and maybe I can bring that to the table if anything. There's some legal information which I'm supposed to flash. So if you look at what you heard about in the last couple of days, the main goal of this research line is it's fundamental research, and it's asking at the core always the question, how does it work? So how does cognition emerge from neurons in the brain? And it's driving in that direction. Application-oriented research, while is also asking that question sometimes, but the primary goal is really to figure out, can we use it to solve any kind of problem? So in our particular case, we're trying to use neural dynamics and dynamic field theory somehow to solve problems. And what that means is, can we build a product? Can we come up with a new technology that solves problems and creates value for people? And it does so better than any technology that exists at the moment. And better means can it be faster? Can it be more efficient? Can we be more accurate, more flexible? Or can we maybe even go into application domains, solving problems that weren't even imaginable to solve before, because we're now using different methods. If we're looking at DFT, the most fitting problem domain is probably autonomous robotics, because of the way DFT is has been thought up, where it is based on the idea of embodied cognition, that cognition is intimately linked to a body, to having sensors and motors, and it all playing out in a closed loop. And then the problem that it's trying to solve is, how can such a system create behavior? And that's the same problem that you have in autonomous robotics. If you think of robots, most people go for this kind of image in their head. You have some humanoid that walks around town or your home and helps you with certain kind of tasks. While that is maybe a nice vision, it's a bit futuristic. We are currently looking more into things that are already in existence, like autonomous cars. They are really autonomous robots. They drive around, they have to navigate, they have to react. They have sensors and motors. They have to react to their environment, and depending on what comes in view, do different things. Even more critically, maybe for our kinds of applications are drones, because they're very constrained. I'll talk about that in a minute. So similar kinds of tasks, but a bit more tricky. But then also applications where you are in a company warehouse scenario, and maybe you would like to have a robot that can fetch things from a particular place in a warehouse autonomously, maybe even help in assembly tasks so that humans can coexist and collaborate with humans, and robots can collaborate on the same floor, which is tricky at the moment. There are a lot of challenges to applications in robotics, and most of them at the moment are still probably just open research questions. So a lot of them, and I won't talk about that much. You've heard a lot about these in the last couple of days, where it's not really clear how perception works, especially active kind of perception, where you try to frame situations in certain ways. It's not clear how abstraction works, not really how you communicate about abstractions. Learning is, well, we do a lot of training at the moment in machine learning, but autonomous learning is a completely different thing that needs to be tackled, I think, from the ground up. And then autonomy, what that means for robots, is also, poorly understood. For us, so these are things that are probably going to take years, decades to figure out. The application timeline is a bit shorter, right? You have to try to come up with things that solve problems now with the principles and insights that you have now. But even there, you have quite a lot of challenges, in particular when it comes to robotics. So if you think back to the drone example, if you want to put any kind of algorithm, any kind of computation onto the drone, you're very, very constrained in terms of the size of the computer that you can put on there, right? If it's too large, the drone won't fly. If it's too heavy, the drone won't fly. If the computer takes up a lot of power, then the drone may fly, but not very far. And that is often summarized as swap constraint, so size, weight, and power. And then you also have a constraint, in terms of speed, where robots, drones, and other kinds of robots, they have to be able to react very quickly to changing environments. And that's not only true for, or all of these are not only true for drones, but for other kinds of robots to a certain degree, right? In an autonomous car, you can probably get away with more size and weight, but smaller would be better. And these challenges come in part from a mismatch between the kinds of hardware that we are using and that we have been using for years, and the kinds of things that we now want to use in terms of methods. So if you compare CPUs that are the most common computational unit with neurons in the brain, you see that they're almost completely opposite. So in a computer, you have just a few CPUs, 4 to 8 cores or something like that. Neurons in the brain, you have on average about 86 billion. CPUs are super fast. So this is from a number I found from one of the top computers a few years ago. This is 2.3 million instructions per second. A neuron is very slow compared to that. So time scale of 10 milliseconds, you have about 10 spikes, bring up a new spike. Not much going on. You have in the CPU sort of a medium functionality set. You have about 100 instructions that you can apply to input, maybe do things without input. Whereas neurons there are different types of neurons, but they don't do many different things. You can model them with just leaky integer and firing things, but very minimal. Then in CPUs, you have random access memory, where you have the infrastructure to access any kind of information in the system, in registers and in RAM and all the way to the hard drives, and you have to have the channels in place for that. Neurons, the only memory is in place, so they only have access to local information. And it's this mismatch that that will lead, if you had hardware that was developed to support these kinds of neural networks, maybe we wouldn't have the kinds of, or maybe we could build better systems with that. And that's the main idea of neuromorphic computing, is to really fundamentally rethink hardware based on findings from biology and neuroscience to arrive at systems that are hopefully much more energy efficient, much faster, and potentially even give you novel functionality, or at least allow you to go into new application areas. So novel functionality is a bit tricky because CPUs are Turing complete. You can do anything with them, but maybe you are then constrained because of energy and speed, and cannot go into certain areas. Neuromorphic computing is a very heterogeneous research area and community. It began in the late 1980s with research into sensors. I'll talk a little bit about that. And then later processors. And today we're using these devices and trying to develop neuromorphic algorithms and applications, while also trying to build other kinds of devices at the same time, and sort of bootstrapping ourselves. So heterogeneous community, let me give you sort of a brief overview. So there are neuromorphic sensors. The most important or most famous one is probably a vision sensor, the dynamic vision sensor, DVS. There are different types, but here's one example, the DVS data camera. And this is a video, of a DVS and recording. I'll just play it for a bit. So you can see that the DVS produces just a regular black and white image in the background. So that's a grayscale image, but that's not the main output. That's really only to sort of have a ground truth. The actual main output is what is highlighted here in green and red. It's a stream of events. So it doesn't actually produce frames, but it produces events wherever a pixel changes its brightness value, so its luminance. So you have, I believe it's 640 by 480 pixels, and at every pixel you continuously monitor the brightness, and when that changes and exceeds the threshold, either getting darker or getting lighter, it then sends an event, and the event communicates the coordinates of the pixel and then the polarity. Does it get brighter or darker? And you can see that then generates very sparse data. So if, I think there's a section here where it's only showing the events here. There's some spurious events all over because you have some noise in the system, but then most of the events really come from this football which is being thrown right here, right? And then some events here from this human, the guy catching the ball. And that's much sparser data than the grayscale image in the background from the regular frame-based camera. You can also see that it has a much higher temporal resolution. So if I go back here a little bit, you can see that if you look at the grayscale image, you can actually see the individual frames. Flip, flip, flip. So that was 3 frames. It's probably like 30 frames per second, what usual cameras do. But in the same time, you get a continuous stream of events. You can also see that it's much more accurate in terms of where the ball was actually at well, it's hard to tell from the frame. So you can imagine that if you want to track fast objects, fast movement, this is much better. Also, it has a much higher dynamic range that can't be seen here very well, but there's another video if you go to this address, which has a whole bunch of cool videos showcasing this sensor. There's a video of a guy wearing sunglasses, and you can actually see him blinking because it then produces events, and that it's barely visible in the grayscale image. Yeah, so that's the DBS. There are all other kinds of neuromorphic sensors for audio. There's a silicon cochlea, so that mimics what happens in your inner ear. So the organ that translates sound waves into frequencies and then communicates that to the brain. There are olfaction sensors, so for odors, picking of smells, and haptic sensors, that's touch. You can actually also do that with the DBS. So if you have some kind of, I don't know, some surface that can be distorted by touch, you can point a DBS camera at it, and then you have sort of a makeshift haptic sensor. There are sensors like that you can buy, but there are other types. Right. So this is where it started. Neuromorphic engineering, it was called back then, and it then at some point started that people develop processors, and here's also where the heterogeneity shows up. There are a lot of different designs from different groups, different technologies. So you have in industry, Intel is producing the Loihi chip. It's a neuromorphic processor. IBM has the True North architecture. There are a lot of academic labs that work on different systems. University of Manchester and Zurich and Heidelberg have their own systems. There are now also a bunch of startups that often work on edge devices with sensors integrated into it. I just put a few names here. And they use different technologies. So Loihi, for instance, is a completely digital chip, whereas I believe the Rolls chip is like a mixed signal, so that has analog and digital mixed up. Brainscales is an analog chip. And then there's also research into new materials, so using things like memristors to directly have the neural dynamics in the material itself. There are some core principles. If you look across the span of things that neuromorphic computing is, some things show up all the time that I believe are at the core, and that is to use event-based communication. So to only communicate change, like in the camera, you don't communicate everything, but you only communicate when something changes, and that then leads to very sparse data, and ultimately leads to energy efficiency. The second thing is massive parallelism. So you have dedicated circuitry for every neuron, for every pixel, and that in the end just gives you a lot of speed, because these things can very often be just run in parallel. It shares the core principle of connectionism, where well, it's often just neural networks where you have minimal units, and the overall function emerges from how they're connected. That also gives you modularity, because you could have two networks that are on the same chip with two different functions, and they're just modular. Recurrence or recurrent connections can be used and are used, for instance, in DNFs and attractor networks. You can use that to get functionality, with fewer neurons than you would with deep networks. And then learning is a core principle, and by learning here, I mean local learning rules. So rather than have backpropagation training where you need information about the entire network, these are learning rules that just target or just access information of, let's say, two neighboring neurons, two connected neurons. And there's a lot of research into that in neuromorphics. and also then support in the heart rate, as you'll see, Louis has that. Okay, so let's maybe have a look at neurons. Now you looked into the dynamics of a field, dynamic neural field, and you'll see that the dynamics of spiking neurons, in particular, the leaky integrated fire neuron that is actually being implemented in silicon on Loihi, it's very, very similar in terms of its equation. So, and I think Gregor flashed this, I believe, in the first lecture at some point. But let me maybe reiterate this here. So spiking neurons, this is supposed to be a neuron, and it receives a bunch of inputs. The inputs are spikes, and then the output of the neuron is also in terms of spikes, right? So it only communicates when there is some interesting event, otherwise it's just silent. And a spike is sent out. You can see that here. This whole thing is just for a single neuron over time, and there's one spike sent here. And this happens whenever the membrane potential, the voltage, exceeds a threshold, and then the voltage is reset to its resting potential. And here it's just done algorithmically. You can also see that the voltage has some kind of decay on it, right? It just decays over time. And that actually comes from this equation. If you look at it, it's pretty much the same as the field equation. So you have here, it's called V, it's the voltage, but you have basically your U dot equals minus U, right? There is the time scale, it's done a bit differently here in for the neural field, it's on the other side, and then it has to do with the entire right side. It's a detail we can skip over. But this is where the decay comes from. So it has this stability property. The input is done a bit differently. In DFT, you would have your input here just added on, and the input would come directly from other populations, right? Here, the input is actually another dynamics, which is the current of the neuron. And the current also has some decay. I didn't put the equation here because it's done a bit differently in the Loihi paper. You'll see it's formulated in a weird way. But it's pretty much U dot equals minus U, something like that, for the current. And the current is whenever an input spike comes into the neuron, the current jumps up and then it decays down. And the current is then drives the voltage up. If you have a bunch of input spikes, the current keeps adding up, and at some point drives up the voltage to produce a spike. And whenever the voltage is reset here after a spike, the current is not. So you have some memory here over longer time scales in the current dynamics. This is what's implemented on the chip in our Loihi chip, and then also similar things are implemented on other chips. I'll focus on Loihi and give you sort of an overview of what that looks like. So we're producing this chip here. That's a photo. This is a sort of a plot of the die, and this is a diagram of what the different elements are. Chip is just like looks like a regular processor, and these elements here, which are visualized here as these yellow squares, are neural cores. So on the chip, you have 128 neural cores. Actually, that's 128. And in every neural core, this is where the neurons sit and the synaptic connections. Every neural core, it's an asynchronous hardware design. You have hard-coded neurons, so they're basically baked into silicon, the equation that I just showed you, but there's also a way to program different neural models with a somewhat restricted, it's like an assembler kind of language, to give you some flexibility. There's also a learning engine where you can program learning rules, local learning rules, for every neuron, basically, or for every synapse in that case. And then for every neural core, you can have up to 8,192 neurons. And that gives you, with these 128 cores overall, gives you a maximum number of 1 million neurons on one chip. There's also 6 embedded processor cores, which are these blue ones here. These are really just x86 processors, so you can run regular C programs on this. And this is good for interfacing with the chip. If you want to feed data into the chip and you maybe then want to encode it in a certain way or decode it, you can do that here in C code. You can, of course, also do that on whatever other computer you're connecting, but you can do it on the chip directly also. You can also do network configuration with code here. And then there are 2 input-output cores, which also have an asynchronous design, and they are very efficient ways of getting spikes into and out of the chip. If you, for instance, want to stream this somewhere else, like to your laptop to have a plot or something. Then these circles here in the middle and these little lanes are sort of the highways for information. So this is the network on chip fabric. I won't go into the details here, but this is to enable communication between the neural cores. So if you have neurons that sit onto these different cores, they send spikes, then the spikes go across this mesh. They're routed across the chip, similar to packages in the internet. And other messages also to synchronization messages and management messages are also sent across these pathways. And then there are 6 parallel off-chip interfaces, these boxes here on every chip, that enable you to link multiple chips together. So you can take, you're not limited to just one chip, but you can stack chips next to each other and connect them with these parallel I/O ports. And then you can, now with this second version of Luigi, you can also go in the 3rd dimension and stack it upward. And that enables you to build very large systems, right? Then the different chips then act as one large system. There's some overhead in communication between different chips. It's a bit slower than going from core to core or inside a core, but you can build large systems. In fact, so this is for Luigi 2, which we released late last year. And before that, there was a previous iteration, Luigi 1. And for this, we had systems. For Luigi 2, they're still in development. So what you may have seen somewhere also in the media is these kinds of devices, different form factors. So the smallest one is this one in the middle. It's called Kapoho Bay. This has 2 chips on board. It's like a USB stick. It's this size. It's a bit larger than a USB stick. So it has these 2 chips on board, and then it also has an AER interface for to connect the DVS camera directly onto the chip. You can plug this into your laptop and then run neural networks directly on the chip. And this was Luigi 1. So on this, you would have something like 120, I think 256,000 neurons. Luigi 2 has more neurons per chip. And then, so this is ideal for robotic applications, right? You could plug this into a small robot and then, like a drone, you can fly around. It's not very heavy also. For larger robots, maybe still, we have these boards, an Nahuku board. This has 32 chips. It also has a host system with an FPGA attached to it, so you can do more fancy things if you want to. And then these integrate into this Bohiki Springs system, which is a rack-mounted server, really. And you can sort of see the different boards. So these are all Nahuku boards in here. And this system gives you 768 chips, so a whole bunch of neurons. This is, of course, not suitable for robotics work, right? This has to sit somewhere in a computing center, and you can access it through the cloud and do computation there. It's for different use cases than what we're aiming at with DFT applications, for instance. But it's working and it's accessible. Good, and we program this through software. We have a software stack. It's an open source project that we've started where we trying to unite the different labs and different parts of the community, of the neuromorphic community, to use the same tools because it's so heterogeneous. So we've started this open source software framework which we call Lava for neuromorphic computing. So this has support for developing neural network, spiking neural network systems applications, and it marries this with the idea of a middleware, where the system that you build is somewhat agnostic to the computational devices that you use. So you could build a network and then deploy it either just on your laptop in simulation, or you could run parts on a neuromorphic chip or part on a GPU. And as a user, you wouldn't have to reconfigure a lot. It would take care of all the message passing and so on. At the moment, it's quite young. Version number is, I believe, 0.4.0. It supports execution on Loihi 2, which is a very recent development, and on CPU, so you can simulate things on your laptop if you just want to try it out. And it's Python-based. Most of it is open source and freely available. You can have a look at the website, which also has a little bit of documentation, and then the GitHub page. In order to use Loihi 2, since you need hardware, there's a process for that. I can talk about that in the end. But the code for that is not at the moment available. It may become available later. We're still discussing how to do that exactly without revealing details about the hardware. So in Lava, very briefly, it's actually in spirit very similar to Cedar, just that it's Python-based and doesn't have a graphical user interface at the moment. But what you build or what you use as building blocks they're called processes here, and they have inputs and outputs, just like a processing step in Cedar would have. They also have these internal variables that hold state of whatever process you're building. It's maybe a bit different. So that for leaky integrated fire neuron, that could be the voltage and the current. And it's then, as a user, you only know about these things. And how it's implemented, it can be implemented in different ways. It could just be a description of the structure of a neural network, which is then run on a neuromorphic device, or it could be implemented by regular program code in Python and C, or it could just be a peripheral device, getting input from the camera. In working with this, it's relatively straightforward. So if you wanted to build something like this, you have leaky integrated fire neurons here, some connectivity here. That is also a process, which I find a bit weird, but so this is all-to-all connectivity, and then some spikes that are injected through the connections into the neurons. The kind of code that you would write is, you build these processes, you create objects for them, you pass some parameters in, you then create connectivity by calling connect functions on the ports. So this guy here has a port that's called spikes out, and this then connects to here, which is this input port for dense. That sets up the connectivity, and then you just call run on one of the processes, which you can do here. You then specify how long it's supposed to run for and how it's configured. And this is sort of where the magic is, where it then automatically tries to, depending on what kind of configuration you give it, tries to figure out what kind of implementation am I going to choose. Am I going to run this on everything on Loihi, or parts of it on your laptop, parts of it on a GPU? It also depends what these processes support. So some, like the lift neurons may not even be supported on particular hardware. And then you can stop it. So that's sort of the bottom layer, and Lava is supposed to take care of all the message passing and all that. on top of this, we're building libraries, which give you a higher level interfaces for different use cases. So one of them is called Lava DNF, which is really DFT. This is something I'm developing. This is giving you convenience functions to design neural populations with attractor states, like something like this, which you're now familiar with, and then build architectures from that. There is a deep learning library, which enables you to do offline training, so direct training of spiking neural networks, and also accelerated training using rate-coded networks. So here's an example where we we trained a network to solve the PilotNet data set, where you have to, from the sort of dashboard camera of a car, have to predict the steering wheel angle. And then there's an optimization library, which is sort of still developing, but this is for modeling and solving optimization problems. So there's a way of solving optimization problems with spiking neural networks. And we did this not in Lava, but before. We had a project to optimize train schedules for the Deutsche Bahn, the German railway company. And we did this with spiking neural networks. Right, so that's the sort of libraries. And I want to go now shift this a bit toward DFT more and show you some of the initial things that we've done on implementing dynamic neural fields on our chip, or at least with spiking neurons. By the way, you can interrupt me at any time if you have any questions. I should have said that earlier, maybe. Right, so Neuromorphic DFT, we have started this little project where we are taking the principles of DFT, which are formulated in continuous for continuous dimensions and so on, and implemented that, and it really abstracts away the spiking layer, right? But we are now trying to implement this with spiking neurons to be able to put it on the Loihi chip and then hopefully get some performance benefits from that, right? And we've done that maybe even in a little bit of a very straightforward, somewhat naive way, where we just sample the discrete, dynamic, the continuous dimension with discrete neurons, right? So you can imagine some one-dimensional dynamic neural field. You put individual neurons here. These are leaky integrating fire neurons. Then you connect it up by just sampling from this continuous kernel function. There's an arrow here missing, so that this also has sub-excitation. So this is showing the kernel just for one neuron, what that looks like. And that then already gives you a one-dimensional field. And you can, of course, do this for this kind of Mexican hat kernel. You can do it for selective kernel. And in just doing this and then hand-tuning everything, which you may have some experience with now, you can recreate the basic DFT instabilities, detection, selection, and memory. So these are the things that you've seen. This is actually from the online simulator that all programmed at some point. So this is now a different view of it, where we're looking at a raster plot. These are spiking neurons. The DNF is the bottom pane here. This is 15 neurons shown over time, and every little violet and yellow dot here is a spike of that particular neuron with the index here. The color is just to highlight the spike rate. So if it goes into yellow, the spike rate is high, right? And violet is lower. And then this is input spikes that go into the DNF, just one-to-one. This goes into this neuron. And you can see here that without any input, you don't have any spike output, no activity in the DNF, as you would expect. If you give it some input with a particular spike rate that is not high enough, it also would not create any spikes. This is because the voltage is below threshold. If you then increase the spike rate, you do get spike output, and then also through recurrent connectivity, you create actually stable peaks, 2 peaks in this case, because you have 2 input locations. If you then reduce the spike rate of the input back down to the initial value here, you see that the peaks persist, right? So that shows hysteresis of this detection instability that you are familiar with by now. So this is a stabilized detection instability here. If you then drop down the input at the end here, the peaks then decay. Right? So that's a multi-peak field. You can also do a selective field with a different kernel, which is this kind of thing that then has global inhibition, and it only ever has a single peak. And you can see that here again, the field at the bottom, the input at the top. Input from the very beginning here, or at time step 100, has 2 input locations, but the field only creates a single peak, in this case here at the top. And it then switches only to the other location when the input at this location ceases. It switches over, but it doesn't switch back when we switch it back on. So this shows you hysteresis also in terms of selection, and then we just do the thing over again in the other direction here. The stabilized selection decision. Memory, it's a bit trivial now because it's almost the same as here, just with more self-excitation. You know that the idea is if you have enough self-excitation, you could take the input away and the peak persists. I think you can see that here, that at the end of where here the peaks drop away because we shut off the input. Here they do not, and the peaks persist. That's a working memory representation of the input. You can also do higher dimensional DNFs. In CEDAR, this would look like that. No, it is working. With spiking neurons, implemented with spiking neurons, it actually looks very similar because of the way we are representing it here. So the DNF is shown here as snapshots over time, and the snapshots are shown as I think the spike rate over the last couple of time steps, and you can see that it only ever creates a peak at one location. So this is a 2-dimensional selective dynamic neural field. I believe this has 15 by 15 neurons. And these are again spiking neurons, leaking to fire neurons. And it does have 2 inputs. So these are the 2 input sources. You can see that the input here is at the bottom right and the top left, but it chooses one and then it switches. This is the same drill as before. And we're just here showing that this is the kernel that's used throughout the field. And this is the connectivity matrix that you would get from connecting every neuron in the field to every other neuron. You can see that it's quite sparse. We've also implemented coordinate transforms, which you probably have heard about also, I hope, where you get a representation of relative position of target objects with respect to a reference position, right? And then you have this transformation field here, which is higher dimensional, and this diagonal projection. And we've implemented this with spiking neurons, where you have the target field here. This has a peak at this position. This is spike rate again over some feature dimension, and this has a peak at position 8, let's say here. The reference position is at position 5, so there's a peak here. And then you have the transformation field, which is 2-dimensional. You would have to rotate this by 45 degrees counterclockwise, and then it's read out sort of this way down here, and then projected onto this relational field. And you can see that the relative position of the target is at 8 with respect to reference at 5. That gives you a position at 3. This is then also projected back into here, and that's this line that's a bit harder to see. Doesn't have any function implication. I just wanted to show that you can do the back projection also. We did an initial demo of just a DNF, because a lot of people are also not familiar with this. It's not super functional, but it sort of shows what DNFs could be used for in application at the very early stages. So it is here to stabilize object tracking. We took a pretty crappy object tracker, which we cut out a template of this fish, which is really just a cutout of the first frame. And then we used an OpenCV template matching algorithm to get the saliency map. So basically this convolution of this template with the whole image, this is what it looks like. So it has a good match here where this fish is. Of course, once these fishes move, it's going to be get much worse. And this is also what you can see there. So if we just take the maximum of this saliency map and use this as the tracker result, you can see that here, that's the baseline. Is there a way to play this? Yes. But in the beginning, it looks fine, but then it just starts jumping back and forth, right? If we take this, and you can also see that there's a lot of distractors here, right? It's fine in the beginning, but then there's other matches. If we take this and put it as input, as bias input into a population of, so basically this is a selective DNF, just with bias driven. This then creates a peak, and the peak actually follows this fish. This is the spike output of the field, and if we use this as a basis for tracking, you can see that it's much more stable than the baseline here. It's one of the first things that we did. This actually ran on the chip at some point. And then we had another project. I had a master's student, Leonard Keil, who worked on a visual search project where we tried to replicate some of a smaller architecture, a smaller version of an architecture that all worked on the visual search architecture that you probably also have heard about, where it's about finding objects with particular features. So here's I found that a bit funny. This work, he did this in the pandemic, so he worked at home and he built this makeshift experiment where he had a bunch of items, put them on the floor, and then we put a camera up here. This is an Intel RealSense camera. It's a depth camera, so you get RGB frames, but also depth information. And from that, you can then build a system where you can look for objects with particular colors and particular height. That's sort of what the setup looked like. And then the architecture is like this, and it should look quite familiar. So this is where the camera image comes in, then goes through some pre-processing and is then fed into these three-dimensional dynamic neural fields, again implemented as spiking neurons. And these then represent colors over space. So X and Y is the image space, and height of the objects over image space. And you can then cue different heights and different colors by injecting spikes into these one-dimensional fields and say, I would like to look at for a red object with a particular height. And these three-dimensional fields would then create peaks at the particular objects' locations, read out the spatial locations here, select one of the object locations, and then put that into working memory. That's sort of the gist of the visual search architecture. Raoult's model, of course, has much more details to model psychophysics also. Here's one of the results. I know this is super overwhelming, but this just shows what happens when you queue for different features. This is what it looks like from the camera's point of view. So you have a bunch of colored objects here. This is the depth map where dark colors are closer to the camera and light colors are farther away. And then you can look at these different slices. There are different time steps. So they're just different situations. This is without any input, which is not that interesting. Here, we're putting in input and we're queuing the color feature of green. So we're looking for a green object. We're not specifying a particular height. What you can see then is that the color space field, this three-dimensional field that codes for color, if you project it onto just the space, you can see that there are some spikes here at a particular location at the top right, and that's actually where this green pot is. So this has a peak at that location. The height, since we haven't queued anything, doesn't produce any output, and then the system is set up to only react when both features match. So this doesn't pick out anything. Same happens if you just queue for a particular height, but not for color. If you do both, so you queue for green and a particular height here, you get a peak here in where we had it before, but then also in the field that codes for height. And then this picks out down here the single position again where the green object is. And then you can do different combinations. This looks for something bluish at a different height, and then that picks out. You can see that down here picks out this blue white weight and the box of the RealSense camera, which is also blue. Another result is that you can do working memory things with this. So if you over time have a bunch of objects, you occlude one of them, and then it reappears. You can see if you look for this blue object with the particular height, it picks out this object, I believe here. It puts it into working memory. If you then occlude it, it cannot see it anymore, even though the paper is somewhat blue, but the height doesn't match because the paper is much higher than whatever this cup, I think it's a cup, was. But the peak is still there in working memory. And if you then relieve it from the occlusion, you get it back. Yeah, I'll skip over this. I just wanted to say that, oh, maybe not. So we implemented this with a spatial resolution of 32 by 24 neurons. So that's in image size, and then 10 neurons for every feature. And if you count this up, you land at roughly 18,000 neurons for the entire architecture. And that's for a very low resolution. If you scaled up the resolution of the camera or the image space to 320 by 240, you'd already land at 1.7 million neurons, which is too much to put on a single Loihi chip. And that resolution may not be necessary, but this is also a small architecture, right? If you build larger architectures, you at some point run into problems with resources again. So in terms of number of neurons, in terms of the number of synapses that you can have, there are other constraints, how many synapses you can have between different cores and so on. So this is a constant pressure that we have, that if we want to build something, it has to fit on a chip. Of course, we could build it and put it into one of those rack-mounted systems, but then you can't put it onto a drone, right? So you're very constrained in that way. So that's something that we're working on. There's some things that we could do is make the DNF implementation that we have more efficient, possibly finding a replacement for the rate code that we're using, because you saw that earlier, when there's a peak, the field continuously produces spikes all the time, and that's always costly. Every spike is costly. If we could find a way to do it with less spikes, that'd be good. We could try to optimize for the number of neurons and the number of connections. That's particularly interesting for the coordinate transform, where you very quickly get into very large number of neurons. And also for higher dimensional DNFs in particular. So if you have, for instance, a 2D input, then you get this 4-dimensional transformation field, which can very quickly blow up in terms of neurons. There is some work, all worked on this to combine DNFs with very powerful perception front end. And that is something that we probably need very quickly when you want to go into real world scenarios to be able to recognize objects. So that's an idea of combining things like convolutional neural networks as a front end for object recognition with these DFT tools and put that on the chip. And there you always, again, even small convolutional neural networks are very large compared to what we can put on the chip. So that's also tricky. Incorporate learning into DFT elements. That's something that Julia is very much interested in, that we're driving, and then make all of that available through DNF, so Lava DNF, our library. Overall, we're always working on building. We're trying to combine all these things to build architectures for autonomous robots, and then build applications around that. At the beginning, or right now, more as demonstrations what you can do with neuromorphic computing hardware, but then very quickly also into actual products. There are some, I've only talked sort of about one arm where DFT matches very well with autonomous robotics and these size, weight, and power constrained autonomous systems. But there are other avenues where we could apply neuromorphic technology, and we have other people looking into other areas, and that's somewhat strange human-computer interfacing things for neuroprosthetics, visual intelligence. You can do things like speech processing, so very well on neuromorphic hardware, and then also very large-scale sort of data center applications where you want to do data analysis and scientific computing using particular neuromorphic hardware. If you're interested in learning more about this, we have this research community called the Intel Neuromorphic Research Community. There's, I believe it's even 150 groups. It's a lot of academic groups and companies who are interested and collaborate with us. There are funding opportunities. You can get access to the hardware, and build up your own projects. So you can send an email to me or send an email to einercinterest@intel.com, and then maybe we can work on some projects. Otherwise, if you're just interested in looking at some of this stuff in terms of software, you can have a look at the Lava website. I flashed that here somewhere. And then maybe just try that. Oh, this is not. Here, I'll maybe stop at this slide so you can have a look at that. Okay, a few minutes for questions.